Hi, everyone. Welcome to this quick recording for the last two basically units for this week. We're in week 13. So we're dealing with basically, we're starting the stars, and last time we introduced some key concepts basically related to their temperature, to their spectral basically properties, and so on and so forth in terms of compositions. And we even tried to come up with techniques to find their masses, because it turns out that the mass is a really critical piece in the puzzle, and we really want to understand that and how it's related to the properties of stars in general and their age and evolution on all of these things. And the technique last time we looked at was the fact that if I have a binary, so if I can determine somehow the Doppler shift for the two stars going in rotation versus their common center of mass, then in that case, I should be able to find the sum of the masses. So that's basically using Kepler's, or at least a modified version of Kepler's third law. And then finding the center of mass, then at the end would determine the masses. And it's a critical piece of information in terms of mass. So today we're building on that knowledge, and we're trying to understand more in terms of how stars are. So let me share with you a screen in here for the next two units, namely 58 and 59. So in 58, basically what we do in this case, we explain the stellar radii, the sizes of stars, and how to measure them. And it's really actually, for the nearby stars, probably it's okay. But for further away stars, it becomes a little bit more difficult. And this is actually one of the hardest things to do for stars in general. And we use the eclipsing method, basically, when you have a binary in this case, and you have a star going in front of the other star, depending on the luminosity of the two stars. If the star that is going in front is brighter than the other one, so in this case, the overall is going to basically hide the bigger, less bright star in a sense. And in doing so, the overall luminosity of the binary drops a little. Okay, compared to if the bright star goes behind the big star, then it's going to drop more, depending on the transition time between the two stars. Depending on how much the dip is, we should be able to find basically the size of the stars. Then again, we're trying to determine methods, trying to find the different properties of stars. So again, so stars are basically too far, and as I was saying, hard to measure their sizes quickly in terms of diameter or radius. And in addition to the fact that here on Earth, we have other conditions that are really can make the things a little harder in terms of atmosphere and things like that. Now, with the advent of the James Webb, we have better tools actually to explore some of these objects up front. So one of the methods basically that is used for telescopes is basically to use the multiple telescopes, two or more, and trying to come up with a technique that if you have, it basically acts as an array of telescopes, okay, compensates for the difference of the waves as they hit and how they interfere. Based on that, you're going to, based on the distance of the telescopes, actually also, you're going to be able to have a better resolution if you wish. So this is the techniques used on Earth. So again, the method I was talking about is the eclipsing of a binary system, in a sense that if you have two stars, in this case, I have one that is hotter than the other one, and the hotter one is actually the smaller one, and you can tell from the colors actually. And if they are far away, then you have a combination, because it's binary, so they are very close from each other. You have a combination of the two lights basically coming to you, to your telescope, to your observation. But then as the first one, the smaller one, the hotter one goes in front of the older one, it hides a little bit the one in the back. So there is less light coming from the one in the back. So at the end, there is a dim. And depending on here, on the depth of how long it takes to go in front of it, that gives me a size, if you wish, of the star. So we have a near transition, and it goes through it, and then it comes out again. Now, if it goes behind, then in this case, because it's a brighter, so there is much less light coming in, so the dip is much deeper, and you can determine sizes based on that. And if you compare the two. So this is one technique used to determine the different sizes of stars. So this units in terms of size is a little bit in terms of yeah, it's not really that long, but the point being in here is this Stefan Boltzmann law. We talked about it a lot so far, and I think for those especially in the lab, we talked about it even more. So it's going to give you the luminosity of the star in terms of how much light you're going to get, how much energy you're going to get per square meter, meaning you have 1 meter on one side and 1 meter on the other side. Obviously, a star is not a square meter size. It's much, much bigger than that. So, but this luminosity per square meter is really the energy per unit time. So it's really the power that is emitted by a star per square meter. So that is the expression for it, and it's a constant, 5.67 times 10 to the negative 8 times the temperature to the power 4. And remember the other law, the Wien's displacement law gives me actually the temperature in terms of the peak frequency as being 2.9 times 10 to the power 6 divided by the maximum or the peak wavelength in this case, provided this number is in nanometers and the temperature is going to come out in Kelvin. T is going to be in Kelvin, and you need this expression also to be in Kelvin. So this is basically the technique used if you can find the color of the star where it maxes. Then in this case, you're going using basically a spectral analysis. Then you're going to find the temperature. Once you find the temperature, you know how much energy is emitted by that star. If you somehow can find the size of the star, then in this case, you should be able to find the total energy emitted. So it should be how bright it is. Now, there is another relationship that they're going to discover between the brightness and the distance, and that is basically take all of that energy divided by the entire sphere that the energy has traveled through, and that is 4 pi r squared, and that is the distance actually to the sun. So from here, we can find actually a technique also to find the distance to the stars. So this is a kind of a light unit, and it's actually a summary of a little bit of the other stuff, with the exception that the introduction of the binary system and how that relates to the stars. So let's get into unit 59. Unit 59 is a big unit, okay? It's going to introduce the Hertzsprung-Russell diagram, referred to all textbook HR. So what the HR diagram is that you have actually a diagram like an X and Y axis, really. On the X axis, you have the temperature, and the temperature follows those classifications: O, B, A, F, G, K, M, okay? Remember, O is the hottest temperature. This is from a previous unit. And then it's going to represent also the luminosity on a scale where the sun is basically the standard, okay? And then this is a logarithmic scale, and we're going to basically, if we take a cluster of stars, like for example, I know some of you sitting in Astronomy 125 right now for the lab, we're looking at the Pleiades. So the Pleiades is a cluster of stars, and you know roughly that they should be of the same age. But if you can determine their luminosity, their brightness, their distance, that this is going to be the same because they're all formed at the same time. So overall, you're going to find some properties. Based on that, you're going to can analyze some of them, and actually some of you did actually do that, are a lot brighter than others. And that determines really how big they are. Okay, because if they have the same temperature, they form the same time. If they have the same temperature because of their peak frequency, actually, and if they have the same distance because they're forming the same location, and if then it becomes a matter of size to determine exactly who's brighter than the other. Okay, so you take those and you classify them, and you start looking at the different colors. So they have all of them the same distance. And you see different colors in here. When you see different colors, that depends on, that gives you also different sizes because of how bright they are. Then you take them and you plot them on this scale, as I was saying, okay? So the temperature is hotter here, and the luminosity is higher here. So on this axis, on the left-hand side, this is decreasing temperature. So this is low T. And on this side, it's high T, high temperatures. So that's the key thing. Other than that, in here, it's actually a scale where the luminosity, basically how much energy is outputted per unit time per square meter, that is actually higher in here. So this is more luminous, and this is dimmer star. So that's basically the in a nutshell. So on the x-axis, you're looking from hot to cold. On the y-axis, looking from dim to bright. That's it. So that's basically the key component for the Hertzsprung, the HR diagram. Okay. So if you plot all of the stars on the diagram, this is how they look like. Again, the temperature is hotter on this side. It's 30,000 Kelvin and plus. And in here, it's dimmer, 3,000 Kelvin and less. Okay. So these are cooler stars. When you see a red color, that's cooler than the blue. That's basically what that is. On the luminosity scale, the 1 is the sun. Remember, the sun outputs something 10 to the power 26 watts per energy, okay, watt. So that is basically the standard. That is the candlestick. That is the one that we measure with respect to it. This scale is not linear, though. I mean, if I go from here to here a step, I don't double the luminance. I 10 times it. Okay. If I go from here to here, I don't basically go by a factor of 2, then going from here to here. I go by a factor of 100. This is what a logarithmic scale is. So a logarithmic scale is, if you didn't take this kind of math, this two, they appear to be equally spaced. So the distance from here to here appears to be half the distance from here to here. If this is a linear scale. In a linear scale, the distances scale up according to the sizes. So this would be 3 times as big as this one. That is a linear scale. In a logarithmic scale, it's a little different. I mean, the spacing is still the same. Okay. But if you go from here to here, versus if you go from here to here, this is 10 times more, not double. This is on a base of 10, because the logarithm can be on any base you like. So 10 base logarithm, like for example, earthquakes. Earthquake of 7 versus an earthquake of 8 is not just 1 unit more, it's actually 10 times more. 10 times more powerful. And an earthquake of 2 versus an earthquake of 5 is 1,000 times bigger, not 3 times as much. Okay? 1,000 times more intense, because the difference between them is 3, which is 10 to the power 3, basically, which is 10 times 10 times 10, which is 1,000. Same thing in here. The luminosity of the sun versus that, for example, of something that is appear 1, 2, 3, 4, 5, 6 on the scale is 1,000,000 times. And you actually have it in the units on the scale on the left-hand side showing. On the left-hand side, it shows you 10 to the power 6. So this is actually 1,000,000 times. This is 100,000 times, and so on and so forth, as opposed to the stars at the opposite scale, which are 1/10, in this case, brighter than the sun. The sun is 10 times brighter. The sun is 100 times brighter. The sun is. So if you scatter all of this, there are 3 things that emerge immediately. There is a line that crosses the diagonal from the top right to the bottom left. It looks like it's like this. We have 3 regions. We have a line that goes like this. I mean, it's a little bit curved, and then there's a group of stars in here and groups of stars in here. This line is what is known as the main sequence stars, and the main sequence stars are stars going through their normal life. And then you have these ones in here that are, look, they're a lot less luminous than the sun, but their color is blue. So they must be super hot. And actually, there is another scale on the same graph in here, which is the size. These are a lot smaller than the sun. So these are the white dwarf. These are the remnants of the sun-like stars when after they run out of basically fuel in their cores. So they end up being small in size, hot because of they just basically came out of that. They collapsed on a very small size. And they're less luminous. They emit less light overall. It's very hard to see, especially the ones that are on the scale of thousands and far away. Now, on the other side of the spectrum, this one's in here. They're much bigger than the sun. This one on the left in here, on the right, I'm sorry, in here, they're actually, their surface temperature is less, but they're super big, super giant, okay? And so they emit a lot of light because they're of size, so they emit a lot of energy, although it's less surface temperature, but they emit a lot of energy because of their sheer size. So these are the giants. You have some red giants in here, and you have some blue giants on the other side in here. These are young stars. They are big to happen to be, and they're going to go very quickly. Most of the times, these ones, they end up in, at least this one's in here, in a scenario other than this one. So this is really actually is how stars die, really. And in here, there is another scenario for them that they can go to, two other scenarios that they can go, either as a neutron star or as a black holes. So this is basically the entire story of this how stars go. So they come in young, they go through their main sequence, they can spend a long time for those in here, small sizes in the main sequence, or a very short period of time for those on the top left, I'm sorry. And they evolve into this region as they grow basically in age. And they can end up in this corner, the bottom, or they can end up, depending on their size, into other scenarios. So this is basically in a nutshell what the HR diagram. As I was saying earlier, the HR diagram also classifies in terms of one important point before I get into that. Very, very important. When you look at the HR diagram, you may be confused thinking that this star, for example, is very far from this star. The one that is on this side, it's on very far from this star. And these two stars are neighboring stars. No, that's not true. For this particular group of stars, they could all be in the same neighborhood. This is how they look like to you. But the mere fact that they evolve in the HR diagram doesn't mean that they move in the space at all with respect to one another. They could be a whole group moving at the same time, one of them exploding, that's it, and went through the entire cycle. This is not a physical positioning of the stars. Okay, so again, these are some of the stars that are known to us. Proxima b, which happen to be a star, the closest star to us, Proxima b, Proxima Centauri, I'm sorry, is actually a little less than 1,000 times dimmer than the sun. So it's a very, very dim star. It's a red dwarf. Dwarf because it's small in size, very small, and it's a red in here. Versus, for example, if you look at Aldebaran, I know some of you were talking about it the other day, especially when we were talking about the Pleiades, which is Aldebaran is the eye of the Taurus, and the Pleiades are actually part of the Taurus constellation also, and happen to be slightly above it. So this is Aldebaran, the bright star that is on in the Taurus, which is the eye of the Taurus. And Betelgeuse also talked extensively about it. Betelgeuse is also a red giant in here. So these are your red giants. Those are going through Arcturus also. We talked about it, at least in the Astronomy 125 in the section. So all of this are red giants, albeit in this case, Betelgeuse is much, much bigger than the other two. Okay. And then you have the yellow giants, which are actually, like, for example, Polaris, which happen to be in here. And we talked about that a lot, even in this class, which is the northern star. And you have others also. One of them is Rigel. Rigel and actually Betelgeuse are in the same constellation. And again, when you see something in the same constellation, doesn't necessarily mean that they are close from each other. And if you look at the at Orion itself, you have the 3 stars in the belt, and then you have Betelgeuse in here, and you have Rigel, and you have Safe, and you have Bellatrix. You have to be careful in here that this positioning is just projection in the night sky. They could be, some of them are much closer to us versus others that are further away from us, okay? Because there is an element of depth that is not represented. But for the case of the Pleiades, for example, or the Hyades, which is another group of stars, then in that case, they're all in the same distance because they're formed in the same distance. As a matter of fact, part of the ones who are doing Astronomy 125, we were able to find, and we should be able to find the distance of the entire cluster, basically, or group of stars. Now, these are white dwarfs. One of them is Series B, and Series B is actually part of a binary system where you have Series A in series B, and A is actually the bigger of the two, but it's a main sequence star. Okay, it's still going through its own age. This one went through already. So this one is a white dwarf, and if you look at them, you will see that basically the two appear to be one star. But then with the far more refined observations, you will see that they are actually two different stars. Vega, which is another star of interest, usually because of the fact that the Earth right now has Polaris as its north pole, north star, is going to spin, and at some point it's going to be Vega. And Vega is actually another interesting star, and it's actually a main sequence star. Proxima Centauri, Alpha Centauri A and Alpha Centauri B is also another binary star, and that we talked about last time in the last unit. This is actually a system of stars that are actually the next closest stars to Earth, if you wish, and they are actually part of a binary. And they are actually, both of them are main sequence stars, and their colors are actually not too far from the sun. Alpha Centauri A is slightly brighter than the sun, versus Alpha Centauri B, which is slightly less brighter than the sun, and sun sits in the middle. Okay, so the entire system of actually Alpha Centauri A, Alpha Centauri B, the sun, and actually Proxima Centauri, some astronomers believe they're actually one big system, albeit the sun is a little bit further away, but they form in the same region altogether. So that's basically some of the studies. You have Bernard star, which is another brown dwarf, but that's actually a red dwarf, I should say. It's actually which is actually not too far star also, but it's actually slightly more brighter than Proxima B. Anyway, so these are the main sequence stars. And these are some of the familiar stars we've been talking about in terms of how they fit on the HR diagram. In terms of size, as I was saying, the sun, again, is the standard. So the sun is one radius. In this case, if you look at Alpha Centauri A, it's slightly bigger than the sun. Alpha Centauri B is slightly less big than the sun. Remember, this was part of the previous exercise in another unit where we determined the mass of A and the mass of B, and we find their sum as being 1.9 the mass of the sun. And then we, based on the other observations, if we determine their center of mass, the common center where they rotate both of them, this is the distance from the star to the center of mass, and this is the distance from distance, I should say, distance star B. You can use this to find the different masses, and the different sizes can follow from the how bright the stars are. As I was saying, Proxima Centauri, now I have this word stuck, hopefully it's going to go away. It's it's slightly less than the 10th of the size of the sun. Okay, remember Jupiter is about the same size. It's about the 10th of the same of the size. So Proxima Centauri, last time, hopefully. Proxima Centauri and Jupiter are not too different in size, okay, in terms of physical size, but in terms of mass, of course, Proxima Centauri is bigger than Jupiter. And again, look at Betelgeuse. It's more than 1,000 times the size of the sun. Betelgeuse, by the way, is not the largest star out there. Antares also is big. Aldebaran also is big. Arcturus also is big. And this is why they're called giants in the part that is red, in giants. Red because they happen to have the same M classifications in here as all of the stars. Then you have the K stars, the G stars, and so on and so forth. So this is an introduction. So the HR diagram has a lot of information in it. It tells us the temperature of the star and which classifications they happen to be, okay? It tells us the luminosity, how luminous the stars are. So two things also we should know: temperature, luminosity, and the last thing we know, at least from here, is the radii, the radius. There is another piece of information that is not clear yet, but we're going to see it soon, and that is the age of the star, the mass and the age of the star, okay? So that is basically another piece of information here. Again, here is the mass. The mass and the luminosity are related to one another through this law. The mass is proportional, so when you see that, it's proportional to the mass to the power 3.5. If you didn't really take a lot of these things, take the mass and multiply by itself 7 times. So that's what we mean by m to the power 7, and take the square root. So that's it. Take the normal square root. This is what that expression is. So in other words, the more mass of the star, the more luminous it is for the same temperature. Okay, so this is basically in a nutshell what this expression is. And this is basically with the same expression. So again, it's L, which is some constants in here. If you scale everything correctly to the sun, so everything in terms of the sun, is m to the power 3.5. If you're not too familiar with this business of powers, just take the square root of m to the power 7. What m to the power 7 is m times m times m times n 7 times. So if you do that, then you basically are in good shape. You are in good shape, and now you have the whole expression for the luminosity. Okay. Thank you. Okay, hold on. I'll be back. Okay. Anyway, that was really the introduction of the 2 units for this. No, the other 2 units. I know we did the previous 2 units, so this is the whole unit, the whole content for this week. And I think we're going to build more on the HR diagram next week, and hopefully we will continue that and get into the whole story for the stars in terms of their age and how they evolve. And we get into actually later on topics such as neutron stars and the different fascinating stuff related to the neutron stars. You have pulsars, you have magnetars, you have all kinds of neutron stars, and you have black holes also, and white dwarfs also, which is part of the evolution of stars. Anyway, I will see you guys next week. And for some of you, I will see you in the lab on Thursday. Thank you. Others actually are sitting in the other lab, which is Tuesday too. So I'll see you on that day too. Thank you.